Morning, Rainisha. We're just getting
morning.
started. How are you?
I'm good, and yourself?
Really good, thanks.
Drop me by when you get them. Drop me by 2.
All right. So tell your mom I said hello.
Of course.
Okay. So here we go. So we're gonna start with by going back through all the MCQ from Unit 6. Okay. So question 1, the chemical reaction between hydrochloric acid and ammonia is represented above. A student combines equimolar amounts of HCl and an H3, both solutions initially at 24 degrees Celsius in a coffee cup calorimeter. The student observes that the mixture reaches a temperature of 28 degrees Celsius. Based on the experimental results, which of the following can be concluded about the reaction? Okay, give yourself just a few seconds to go through the choices, and then we'll talk about which one's correct. All right. What do we think the right answer is, Renisha?
I'm actually still working through it a little bit. If I could get like a couple of seconds.
Okay.
Is it exothermic?
What do you think? What do you think, Jacob? Is this exothermic or endothermic?
I'm thinking it's exothermic
Exothermic. How do you know?
because it's releasing energy into the reaction.
Okay, so then what's the correct answer, Renisha?
The correct answer is C.
There you go. Okay. Yes, because when the temperature goes up, we have an exothermic process. Okay. Heat is exiting the process and warming the solution or whatever it's happening in. Okay. All right. Any questions? Let's move on to number 2. Okay. When pellets of sodium hydroxide are added to a flask of water, it is observed that the temperature of the water increases as the pellets dissolved. Which of the following claims about the observed dissolution of sodium hydroxide in water is most accurate? Okay, so give yourself 30 seconds or so. Take a look. Did you have a good breakfast? Yes, you did. Okay, Symphony, what do you think for this one, number 2?
I think it's C.
You think it's C. Okay, it's exothermic because heat energy is absorbed by the water as the NaOH dissolves in it. Okay, who else got C?
I got C.
Jacob, Rainisha, how about you?
I was torn between C or D.
Okay.
Yeah, same here. I was torn between C and D.
Okay. So since the water is getting warmer, the water is absorbing heat, okay? And that's okay. So the water is absorbing heat, and it's getting, that's an interesting one. Heat energy is released by the water as the NaOH dissolves in it. No, it's really released by the NaOH. That's wrong. So it's C. Let's double check. Yeah. Yeah, because the NaOH is the thing that's breaking up. So you've got your bond between sodium and hydroxide being broken, and so it's the breaking of that bond and the forming of new um, hydrogen bonds between um, OH and water that are fueling this whole thing, and the NaO the sodium's also becoming solubilized in this case. But the thing that's really happy is the OH forming those hydrogen bonds with water. So that's where your enthalpy decrease is coming from. So yeah, exothermic. Okay. Let's go with number. Any questions about that?
No, that makes sense.
Okay, number 3. So an advertisement for a commercial hand warmer claims that the hand warmer works because a chemical reaction in the hand warmer draws out the body's own natural heat, causing a warming effect. Which of the following states the accuracy of the claim in the advertisement and best provides a correct scientific justification of this claim? Okay, this was a fun question. Just take a few seconds to think through it. Peyton, are you there? Can't hear
Oh,
you.
I'm so sorry. I was on mute.
Okay.
Okay. So first of all, we know that the claim here isn't going to be accurate because drawing out the body's own natural heat is going to cause your hands to feel colder. That would be an endothermic process rather.
Yep. Mhm.
So we know it's not going to be C or D. Now, B says that heat flowing from the hands to the warmer would only happen if the chemical reaction is exothermic. Well, that's just not how that works. So we know it's going to be A, and that's backed up because it says, like I said earlier, the chemical reaction is endothermic, causes the hands to feel colder.
Yes, that's correct. Okay. Any
All right.
questions about that? Rainisha, is that what you got? I know you haven't seen this one before, and so I don't know if you've watched our video from last time, but
No, I got A as well.
you got A as well.
Yeah, because the other 3 didn't quite make sense.
Good. Okay. Wonderful. So let's move on to the next question. So transfer between zinc and water. Okay. So a student carefully drops a 9-gram solid zinc pellet initially at 50 degrees Celsius into an insulated cup containing 30 grams of water at 27.8 degrees Celsius. The student predicts the temperature of the water will increase after the pellet is added. Which of the following statements is the best justification for the student's prediction? Okay, so this is a fun little calorimetry question. All right, so give yourself 30 seconds or so. I'll pause the recording. Okay, Symphony, so tell us about this one.
The correct answer would be B because they're both at different temperatures and like they're both 2 independent like things. So once they mix together, they'll transfer energy and yeah.
Yeah, that's correct. So we'll have thermal equilibration here. So systems thermally equilibrate when they're in contact, and so this is absolutely what's going to happen here. Okay, B is correct. Any questions about any of the other ones? Anybody think that one of the other answers might be correct? Okay, then we'll move on. Number 5. Okay, so 2 aqueous sodium chloride solutions of equal volume and concentration were kept in flasks and held at different temperatures. The 2 solutions were combined in a larger flask. Based on this information, which of the following predictions is correct? Okay, equal volume and concentration, combined. Okay, so, oh, this is fun. Okay, all right, so this is very similar to the last one. Take 20 or 30 seconds. I'll pause the recording. Jacob, tell us about this one.
Okay, so I'm thinking it's B. The reason being is it's saying that the cooler solution will increase as it collides with the particles from the warmer solution, which makes sense. C and D looked like good options until you read the last parts where it says that the mixture, what is it? Which the average kinetic energy of the particles in the mixture will be lower than the average kinetic energy than the particles had in the cooler solution.
Yeah.
That doesn't make sense.
Yeah.
And then it's virtually reversed for D.
Yes.
So that just leaves B.
Yep. Very good. Any questions? All right. Let's move on. Number 6. All right, so the table provides data for 2 methanol samples, both liquid. Based on this information, which of the following statements describes what happens when these samples are initially mixed and why? Okay, so give this a read. It's very similar to the last one, okay? Take 20 or 30 seconds. Okay, so we've got this one. Rainisha, tell us what you think.
As I was reading, I eliminated C and D just because when reading them, they didn't make sense in terms of like density, like one has a higher density and two, D and C just didn't make sense. And then
Why doesn't D make sense?
D doesn't make sense because it said that the average kinetic energy of the molecules in sample one is greater.
Okay, what's the temperature of sample 1 versus sample 2?
Okay, I see. Okay, I see that. But I still think it's B. I thought it was B.
No. Sample 2 can't transfer kinetic energy to sample 1 because it's got a lower average kinetic energy. So the
Okay.
thing with the sample or the whatever it is when you're mixing two things of different temperature or when you're putting them in contact with each other, whatever has the higher temperature is going to transfer heat to the lower temperature object, okay? So that's a transfer of kinetic energy.
So, but okay, so the one with the higher. Okay, I see. So the correct answer is D then.
Yes.
Okay,
Mhm.
I see that now. Yeah.
Yeah, something colder can't make something else warmer. So the warmer thing warms the cooler thing, and then they equilibrate to some average temperature. And D is correct because the methanol from sample 1 is going to transfer its heat to the methanol in sample 2. Okay,
Yes, I
that's
see that.
that reason. Huh? Very good. Okay, any questions, scholars? Okay, let's take a look at number 7. Oh, this is a fun one. Okay, so the graph above shows the changes in temperature recorded for the 2 liters of water surrounding a constant volume container in which a 1 gram sample of benzoic acid was combusted. Assume that heat was not absorbed by the container or lost to the surroundings, that the density of water is 1 gram per milliliter, and that the specific heat capacity of water is about 4.2 joules per gram degree Celsius. Based on this information, estimate how much heat was released from the combustion of the benzoic acid sample. Okay, so you've got this happened in 2 liters of water. Okay, so this is a math problem. This is actually a lot like this reminds me of a free response question, really. Okay, so take a couple minutes to do this. Okay, I'll pause the recording. All right, so what do we think? Let's go with Symphony. Symphony, tell us about this problem.
The answer to this problem would be B because
Okay. So I'll do the math on the board here. How'd you get to B?
okay, so you're looking for the heat released, which
Mhm.
means you're looking for Q and MC, and Q equals MC delta T.
Yes.
So the M would be 2000 because yeah, and then the C would be 4.2 because it says specific heat capacity of H2O is 4.2 joule per gram, and then the change in temperature as shown in the graph is 3. So yeah. And then when you do it all together, you get 25 point something kilojoules.
That's what you get? Yeah. So I got 24, sorry, missed a 0. I got 24,000 joules when I did that in my head by, yeah, so that's, okay, there we go. Yeah, and this is an approximation, so they're both approximations. So indicate
So
that.
Dr. J, I understand the process, but I just don't understand how you would get the change in temperature. Would you just take the first point and then the
Yeah.
last point and subtract the?
That's right. Yeah, I mean, I look at the average. So like it starts at 22,
Mhm,
right around 25. So I look at, remember, delta T
mhm.
equals T final minus T
The
initial.
initial. Mhm.
Okay.
Yes.
So 25 minus roughly 22. Okay, any questions? All right, good job, scholars. Let's move on to the next problem. So we've got this guy here. Okay, so for an experiment, a 20-gram piece of aluminum was placed inside an insulated cup filled with 40 grams of water. The data are given in the table above. Assuming no heat is absorbed by the container or the surroundings, which of the following equations provides the correct mathematical relationship for the transfer of heat Q between aluminum and H2O? Okay, so this is a fun one. Just give yourself about 30 seconds, okay? Okay, so Kaiten, tell us about this one.
Okay, so this one was fun because the first time around, this one really messed me up. Because so there's that big old fancy chart up there, and I looked at it for a long time, and I did some math, and then I brought it to you, and you said, "Yeah, that chart's all just spinach." And the reason for that is because whatever heat the mass of aluminum loses, the mass of water gains. So negative Q of aluminum is equal to Q of water.
Yep.
And the rest of those are just red herrings.
Yeah, and it's a reasonable way to do, because Q of H2O, that is going to be a positive value, so leaving it positive makes sense. And then the aluminum's going to lose heat, so making it negative makes sense, because then you have a positive water value. Not that you couldn't say that Q of aluminum equals negative Q of H2O. You could totally do it that way too. Yep, so D. Okay, any questions, scholars?
No?
Okay, so let's take a look at the next question.
This is another fun one.
Yep. Okay, so a student dissolves 8 grams of ammonium nitrate in 100 grams of water in a coffee cup calorimeter. Based on the initial and final temperatures of the mixture in degrees Celsius shown in the diagram above the laboratory setup, what is the calculated change in temperature of the water reported to the appropriate number of significant figures? Okay, so here the real thing is knowing our number of sig figs. Okay, so remember, we get 1 sig fig beyond what's marked. Okay, so look at what's marked, right? You get 1 additional decimal place. All right, so I'm going to pause this, take about 30 seconds to think about which answer is correct. Time we. So, Ranisha, see if you can take a crack at this one for us. What do you think?
So I've been working on sig figs because that's something I'm struggling with a little bit. But from what I'm learning, are you only showing A and B?
Sure,
Because
A, B, and C.
A,
Those
B,
are
and
what's
C,
on the
okay.
board. You can see all A, B, and C.
Okay.
D is a little off. I mean, you're not going to
Yeah,
have
D's off.
big here.
I'm assuming that it's C because
Why C?
when well, either C or B, but I'm thinking C just because it's showing like 20 point something or 25 point something,
Good.
like
Good.
0.1
That's
or
an extra
point something.
decimal place you get. Good, right? So
Yeah.
it's got the tens places marked. It's got the ones places marked. So you get to decide on the tenths place?
Yes.
Very good. Okay, that's exactly right. C. All right, you get that one extra significant figure. Okay. Any questions? Let's move on. All right. So, oh, this is fun. Okay, these pictures represent evaporation and condensation, and so they're called particulate models of evaporation of liquid water and condensation of water. And based on these models, you're going to ask yourself which of the following accurately compares the energy changes associated with each of the phase changes. Okay, and so this is true not just for these models, but this is true in general for these processes, which are reverses of one another. Okay, so go ahead and give this a shot. So I want to hear from Symphony. Symphony, what do you think about this one?
I think the right answer is C because I mean for this specific question, when you look at the graph, I mean 6 molecules are being evaporated and 6 are being condensed, so they're equal and yeah.
Yeah, that's right. So evaporation and condensation are reverse processes. So their energy change values, okay, which we actually call delta G, are reverses of one another, and their enthalpies are going to be reverses also. So the delta H values and the delta G values are going to be equal in magnitude, opposite in sign. Okay. Any questions? All right, Renisha, does that make sense?
Yes, that makes sense.
Okay, let's take a look at number 11 here. All right, oh, these are fun too. Okay, so this is another one this one gets a little mathematical. Okay, so the table above provides the values for some physical properties of H2S and H2O. Approximately, how many moles of H2S must be condensed to release as much heat as would be released when 1 mole of H2O is condensed? Okay, so give this a shot. All right, take, take 30. All right, Jacob, tell us about this one.
Okay, I'm thinking it's C because there's 20 heat capacity on the H2S, and then there's 40 on the H2O. So you
20.
just double it and
There you go. Yep. Exactly. Very good. So 20 times x equals 1 times 40, x equals 2. Uh-huh. That's a simple explanation, but the way you were thinking through it, Jacob, is exactly the way I thought through it. Yep, you got to have twice as many of those. Any questions? Okay, nicely done, Jacob. All right, so let's take a look at number 12 here. Okay, so the heating curve for 1 mole of sodium initially at, sorry, I don't know why I just clicked something. Okay, the heating curve for 1 mole of sodium initially at 25 degrees Celsius is shown at the left. Which of the following best explains the change in heat when 0.5 mole of sodium undergoes the transition shown in the diagram above and to the right? Okay, so here's the transition, right? And there's something going on over here, and then this is what's going on at the particulate level. Okay, so this is our graph, particulate level. Okay, so give yourself a minute to look through this. All right, so let's see. Symphony, tell us about this one.
This one, I'm not sure. I forgot how this one works.
Okay, Kaiten, you want to take a crack at this?
Yeah, sure. So the first thing I looked at was the what is that, particulate diagram, particle diagram?
Mm-hmm.
And it looks like this is sodium going from the liquid phase to the excuse me, to the gas phase. So the place that you see that would be the second.
Yeah, you're right, because it is kind of disorganized there, and it goes
Yeah.
to the gas phase. That makes sense. Yeah.
So the second long flat line that you see between 30 degrees or 30 kilojoules and what looks like 128 kilojoules at 900 degrees Celsius, which I'm presuming to be the melting point,
Yeah.
or rather the boiling point
They
of
really,
sodium.
they really mess with you on the math in this one. So like, okay, so
Yeah.
what you're doing is you're going from here, right,
Uh-huh.
all the way over to here.
Right.
So that's like the change here, right,
Mhm.
is roughly, let's call that 98
Yeah.
kilojoules.
Okay.
But
So that
you said per mole.
per mole, right? That
Yeah.
tells us that to get 1 mole of sodium from the liquid phase to the gas phase at 900 degrees Celsius, you need to add 98 kilojoules.
Per
Now,
mole.
we're not
How many
per
moles do you
mole,
have?
right? We're not working with 1 mole, we're working with a half mole. So you cut that number in half, and that tells you how much it needs to get that from the liquid to the gas phase at 900 degrees Celsius.
Yeah. And that's why B is the correct answer. Yeah.
Right.
Nick. Good job, Kaiten. Yep. All right. Any questions about this one? Okay, that's a really good problem. So please review that one if you found that one confusing for you. Okay, that's a really important problem right there. It just helps keep you on your toes. It keeps you focused, right? Like you got to make sure you get the. This is a little more old school, but it really does keep you focused on all the information. Okay, I'm gonna go ahead and erase this guy, and then we're gonna go to question number 13. Okay, so got this reaction above, and the enthalpy change for this reaction is represented by the chemical equation, or sorry, is the enthalpy chain associated with that reaction is negative 1236 kilojoules per mole. When 2 moles of sodium, or sorry, NaOCl react completely with an excess of Na2S2O3 aqueous and sodium hydroxide aqueous, which of the following enthalpy changes occurs? Okay. So, okay. So this is just mathematical. Think through this, guys. Give yourselves a minute to kind of go through all that. Okay. So, Rainisha, can you take us through this question? Or at least through what you're thinking so far?
I'm not completely finished, but what I'm thinking so far is how to like assemble the problem. So
Okay.
it says that NaOCl reacts completely with an excess of Na2S2O3 and NaOH. So
You've got, let's just pause. So you've got an excess here, you've got an excess here, and you actually got 2 moles of this guy. Okay.
mhm.
So normally, how much heat would you get from this reaction as it's written?
Negative 1,236 kilojoules per mole.
Perfect, right? But that
Yes.
requires how many moles?
That requires 4 moles of
Right.
NaOCl.
Right, but you've only got how many?
2. Oh, so you just divide it in half,
That's right.
which is roughly like around
You just look at the answers, right? It's one of those two.
it's yeah,
Yeah. So which one is it though? Or is heat being absorbed or is heat being released?
being released.
Very good, right?
So it's
Because
C.
the
Yeah,
delta H sign is what?
negative.
Negative. Good job. C. That's exactly right. Okay. Any questions, scholars?
I have a
No?
question.
Yeah, go for it.
Okay, so I got this one right, but I was just wondering if, like, does excess affect the delta H?
No, it just means that there's plenty of the other two reactants, so that there's the limiting reactant is your NaOCl.
Okay.
Yeah. So it means that the amount of heat you get will be limited by this one. By this one. Okay. Okay. So are we good there? Any questions?
Yeah, I'm good.
Okay.
No.
So great. So I'm going to erase the board, and then I'm going to move on over here. Okay. So the chemical equation shown above represents the thermite reaction. What is the approximate amount of heat released when 108 grams of aluminum react with excess rust. Okay, so yeah, okay, so give this a shot. Okay, take a minute. Okay, so the important piece of business here is that the atomic mass of aluminum is 27 grams per mole. Is that correct, Keaton?
Yes. So what that tells us here.
Okay, so then I was actually gonna have, is it okay if I ask Jacob to solve this?
Oh, no, yeah, that's fine.
Perfect. Okay, Jacob, knock it out.
Okay, so we have the 27 grams per mole for aluminum, and it asks us what happened when we use 108 grams of aluminum. That's roughly 4 times the amount of grams per mole for aluminum. And we already have 2 moles of aluminum in the problem, so that means that we have twice as much that's required for this thermite reaction. So we double the delta H, which is 850, and that'll give us 1700.
Yep.
So our answer is D.
Yeah, we have 4 moles of aluminum, and this equation is written with 2 moles of aluminum, so you're doubling the amount of aluminum. So instead of getting 850 kilojoules released, you're getting 1700 kilojoules released. That's right. Any questions?
No?
Okay, let's move on. So, okay. So, perfect. So we got this number 15 here. So the equation shown above represents an endothermic reaction between carbon monoxide and carbon. What is the amount of heat absorbed when 1 mole of carbon monoxide reacts with an excess of carbon? Okay, so this is pretty straightforward. Take about 30 seconds.
Yes.
Okay, so Renisha, you think the answer is B?
Yes.
Okay, why is that?
Because when we look at the reaction with the delta H, like the initial delta H, it's 2 moles of CO reacting with carbon to get 127.3. Here it's asking for 1 mole of carbon dioxide or monoxide.
Mhm.
Carbon monoxide. So you basically just divide the delta H by 2 because you're dividing it in half, because you're only asking for 1 instead of 2. So then you end up getting 63.6, rounding that to 63.7.
Perfect. Okay. So, great. Okay. Let's move on. Any questions?
No.
All right. Number 16. Okay. So, all right. The conversion of ozone to diatomic oxygen is represented by the equation above. Based on the data in the table above, what is the approximate average bond enthalpy for the oxygen to oxygen bonds in ozone? Okay. So, well, the thing you need to know about this one, I'll just as a reminder, is that we're going to treat O2 as OO double bond, okay? And then we're going to treat these bonds as X, right? We don't know exactly what's going on there. So go ahead and give that a shot, okay? Take about 2 minutes. Okay, so Keaton, take us through this one.
All right. So here, yeah, let me get some. How can I annotate on this? Because it'd be. Oh, there we go.
No, okay, go ahead.
Okay. So we know that overall, this is the. No, hold on. There we go. Please let me draw. Oh, wrong color. There we go. So we know that this right here is the overall enthalpy change of the entire reaction. Now, within O2, we know that we're treating this as though each O2 has 1 double bond, and there's going to be 3 of those. So since we're dealing with average bond enthalpy of the reaction, delta H is going to equal reactants minus products. Okay, so we know that delta H is equal to negative 300. And we know that the products are going to be roughly equal to 1,500. Or 3 times the 500 per double bond between oxygen. So you can rewrite that as R equals positive 1,200. Okay, so now we need to find out how many bonds we need to split among it. So understanding that O3 here has a resonance structure, kind of like, it's like that, and then kind of like, and then we do that. There's going to be 2 bonds overall in each O3
Yeah.
molecule.
Very
Now
good.
there's 2 of those. So we know that this is going to be divided by 4. So each bond is going to have approximately a bond enthalpy of 300 moles, or 300 kilojoules per mole.
Yep. That's exactly right. Okay. Scholars, any questions about this one?
I have a question. I'm confused as to how we know the type of, or the amount, not the amount of bonds for O3, but how we know which bond type it was. Cause I thought we didn't know what that was. So
Yeah.
we were solving for that.
So like you've got O, O, O. And no matter what kind of bond it is, right? Each
Mhm.
O is making, so like this, there are 3 bonds in the molecule. So the way that you actually draw it is with resonance structures. So you draw like a double bond here and a
Mhm.
single bond there. And then this one has and then that goes back and forth with single bond here, double bond there. Okay, so those are resonance structures, and the overall structure is really a hybrid that looks more like this, where neither bond is a true double bond or a true single bond. So that's what it looks more like. But when you draw it like that, it's hard to keep track of the electrons. Okay, so we tend to draw resonance structures. And this is all kind of like rarefied explanation from our discussion of Lewis structures. Does that make sense? Does that help, Bernicia?
A little bit, but at least, well, the way I was thinking of it is to set it up kind of like algebraically. So like negative 300 equals 2 times whatever our bond average bond enthalpy, right, minus 1,500. But I'm confused as to why that wouldn't work, or that doesn't get us to our answer.
I think the important thing is getting here, 1,200 over 4. And how do we get to 4? We have to say to ourselves that this is true. We have 2 ozone molecules, right? And each of them is going to have some kind of bond here and some kind of bond here. And we don't know what kind of bonds those are exactly, but we know that there are 2 of them, there and there, okay? And so if you say to yourself, well, each ozone is going to be held together by 2 bonds, and there are 2 ozones, so there are 4 bonds total, then the average bond enthalpy of those bonds can be calculated through this equation.
Okay, that makes sense.
There we go. Okay. Yeah.
Yes.
I like that way of doing it. Okay. Okay. Other questions? All right. Then, Kaiten, if you wouldn't mind erasing your annotations, very nice.
Oh, there we go.
And then we're gonna look at this one. Oh, this is another fun one. Okay. So this is methane combustion, and you've got the reaction right there. So the table providing the bond enthalpies, and what the question asks is, which of the following provides the mathematical procedure to estimate the bond enthalpy per mole of O2? Okay, so You're just trying to find the bond enthalpy for O2. And again, the important thing, right, is that when we're dealing with bond enthalpies, okay, overall enthalpy equals reactant bond enthalpy sum minus product bond enthalpy sum, okay? So go ahead and we just shorthand that for reactants minus products, but that's what that means. So go ahead and give that a shot. Take a couple minutes, okay? Take a couple minutes. All right, so Symphony, see if you can take us through this one.
Okay, so for this one, I have A because if you're doing reactants minus products, then you first have to have the total enthalpy of the entire reaction. Then you add the average bond enthalpy for the CO2. And I mean, no, wait.
Yeah, this is a little bit ugly. Like, let me put the math up here because it's just so darn ugly. So normally what you would have is like you'd have negative 802 equals reactants minus products, right? So reactants minus products. Okay, well, what is that? So negative 802 equals, what are the reactants, Symphony?
CH4.
Okay, and let's go ahead and write that down, right? So that's 4 times 4, 14.
Wouldn't it be products minus reactants though? Because none of the answer choices have 414.
Yeah, we'll get there. Plus O2, right? So like you got 2 O2, so 2 times the O2, right? Minus the products. So you've got CO2, and you've got one of those, so 799. And then minus again, you've got 2 OHs, so you've got 4 times 464. Okay, so that's what you would get, right? But you want to solve for this O2. Okay, so what you're going to do is you're going to subtract the 4 times 414 from both sides, and you're going to add these other ones to both sides. Okay, and then you're going to multiply by 1/2. And when you do that, you do indeed get A. Okay, except somewhere along the lines, why did I got 1799. Oh yeah, because there are 2 of those things. That's right. That's correct. You got two CO, you got CO2, so you got 2 of those guys. Yep, that's right. Okay, so A is correct. Yep, and you got that right, Symphony. Nice work. So does that make sense now?
Yeah.
Okay, I just solved it differently than you did. Any questions, scholars?
Nothing.
Nothing. Okay. Oh, Rainbow's got a question. She says, "Daddy, can you give me a snugglito?" I say yes, Rainbow. Okay, so all right, next one. Okay, number 18. We're doing a great job, but this is a lot of material. This took us about 2 days to get through the first time. Okay, so the formation of hydrogen chloride gas is represented by the chemical equation H2 gas plus Cl2 gas yields 2HCl gas. Based on the bond enthalpy data in the table above, what is the approximate enthalpy change for the whole reaction? Okay, so yeah, go ahead and give us a shot. It's a lot like the last one. Take a minute. Okay, so Jacob, can you take us through this one?
So we have the H2 and then the Cl2, which are both breaking to form HCl or 2HCl. So with that, we know that we have the 436 plus the 243. And then on the other side, we have the HCl, which is forming twice. So that means that we have the 432 times 2, times -2. And all of that, yeah, equals -185.
Very good. Okay. Any questions, scholars?
No.
Okay. Very nicely done. And then let's take a look at number 19. Okay. So calcium carbonate decomposes according to this balanced equation. Based on the standard enthalpies of formation provided, what is the approximate enthalpy change of the reaction? Okay, this shouldn't take more than about 30 seconds or so. So go ahead and give it a shot. You got this.
Reactants, right?
That's right, Rainisha, products minus reactants.
So you would do CO2, which is negative 390, plus CaO, which is negative 640.
Okay, so products minus reactants, good. So Ca is the negative 640 plus
And we'll do
390.
those two minus negative 1210, which ends up giving you B.
No, it's 180. Did I mess up the math? Did I give up the math? How did I give it back? Oh, but it's got 3. Oh, I see. I copied that wrong. 390. Okay. So
Jay, is your dog helping you with the complicated math?
yeah, she's my ace in the hole.
Yeah. Hobie's like that too. He comes out and lies on top of my calculus notebook while I'm reviewing.
There we go. Okay, that's the right calculation. Good job, Rainbow. All right. So any questions about that one, scholars? Okay.
Yeah.
So I'll erase that and we'll take a look at number 20. Based on the information above, what is delta H naught for the reaction here? So, okay, we've got SO2 turning into SO3. Go ahead and do the calculation. Should take about 30 seconds. You got this. All right, so Symphony, why don't you knock this out for us?
So for this one, I subtracted, I put negative 395.2, which is the
Good.
SO3, minus negative 296.1, which is the enthalpy of SO2, and then of course the oxygen doesn't count because it's just 0. So once you do that entire calculation, you get B, which is negative 99.1.
Yeah, that's right. Okay. And again, we were dealing with heats of formation. So delta H equals products minus reactants. Okay. The sum of the product heats of formation minus the sum of the reactant heats of formation. Okay. And that's a great stopping point for today. So we'll do 21 through 24. Sorry, any questions about this?
No.
Okay.